unit vectors and projection of vectors. So a unit vector is just a vector that has a magnitude of 1. Let's have a look at an example of a vector that does not have a magnitude of 1. Let's look at the vector 3, 2, which of course can be written as 3i plus 2j, and we'll call this vector u. Now, a unit vector would be a vector that's parallel to this vector, but has a magnitude of 1. And the way we can find a unit vector from a given vector is that all we have to do for a unit vector is take a vector and divide it by its own magnitude. Because you can think about as dividing its own magnitude as like cancelling out and simplifying to 1. So let's have a look at this vector and how we can do that. So first we need to find the magnitude of the vector. So let's find the magnitude of u. And that's just going to be the square root of 3 squared plus 2 squared, which is going to be root 9 plus 4, which is root 13. So the unit vector that'll be parallel to u, so another way to think about it is u hat, is going to be the vector itself, 3i plus 2j, divided by its magnitude, which is root 13. And another way to write that is 3 over root 13 I plus 2 over root 13 j. And we can verify its magnitude is 1 by looking at the magnitude of u hat. So we get the square root of 3 over root 13 squared plus 2 over root 13 squared. That's going to give us root 9 on 13 plus 4 on 13, which is root 13 on 13, which is root 1, which is in fact 1. So we can see that we've successfully created a vector that's parallel to this vector and has a magnitude of 1. Now we're going to look at projecting vectors onto each other, which we've spoken a little bit about in the scalar dot product. So let's have a look at a couple of vectors. Let's have a vector u and a vector v. And if we're going to project v onto u, we need to make a 90-degree angle from v to u, and then draw in this vector here that successfully projects v onto u, so which will be this vector here. And that vector we're going to call p. And we want to be able to find an expression for p, so find a vector p which projects v onto u. So another way to write p, we could say that it is the projection of v onto u, like that. That's another way we can write it. So projecting v onto u. Now, if we had the angle between u and v, well, let's call it theta. We can write some expressions down. So we can say that cos theta equals our adjacent side. So you've got to be careful not to put p, but the magnitude of p, because we're after the length of p over the hypotenuse, which is just going to be the magnitude of v. We can also write that the dot product of u and v is the magnitude of u times the magnitude of v cos theta. And let's go ahead and make cos theta the subject. So we get the dot product of u and v over the magnitude of u times the magnitude of v. Let's go ahead and equate these two equations. So we get the magnitude of p over the magnitude of v equaling the dot product of u and v over the magnitude of u times the magnitude of v. The magnitude of v's will cancel out, and we get an expression for the magnitude of p will equal the dot product of u and v over the magnitude of u. But this hasn't successfully gotten our expression for the vector p, only its magnitude. But that's a good start, because now all we have to do is multiply the magnitude of p by a unit vector that's parallel to p, which is also parallel to u, and that'll get us the correct vector for p. So we need to go ahead and find a unit vector that's parallel to u. And we know how to do that, because a unit vector parallel to u is just going to be u over the magnitude of u. And so to get the vector p, all we need to do is go ahead and multiply our magnitude of p by the unit vector that's parallel to u. So we can get an expression for p, saying we know the magnitude of p is the dot product of u and v over the magnitude of u, multiplied by the unit vector parallel to u, which is u over the magnitude of u. And just rewriting this, we get the dot product of u and v over the magnitude of u squared times a vector u. And this will successfully give us a vector for p, where you can think about u dot v being a scalar quantity, because the dot product always gives us a number. The magnitude squared is also a number. So this factor gets multiplied by our u to give us our p. So let's go ahead and look at an example. So let's draw up our xy axis. So we're going to look at a vector u being 5i minus 12j, and another vector four I plus 3j. This will be vector v. And we're after the projection of v onto u. Which we're expecting you're bringing u down. Not sure if it's going to be on which side it's going to be on, but it could be something like this, and we could be expecting something like this. It might be on the other side. It's hard to tell with this diagram. So if we're projecting v onto u, we know that's going to be u dot v over the magnitude of u squared multiplied by our vector u. And if you were projecting u onto v, the only thing that would change is this would be v, magnitude of v squared, and this would be v. So you just got to adjust if needed. And yeah, we're after this vector here. This vector here with the projected vector of v onto u. So to do that, we first need the dot product of u and v. So that's going to be 5 times 4 plus minus 12 times 3. So we're going to get 20 minus 36, which is minus 16. Then we need the magnitude of u, r squared. So the magnitude of u squared, so if you're finding the magnitude of a vector squared, that's just going to be its x component squared plus the y component squared. You don't have to square root it. You do if you're finding the magnitude, but not the magnitude squared. So that's going to give us 25 plus 144, which is going to be 169. And then finally, we can work out our projected vector, v onto u, as our dot product, which is minus 16, over our magnitude of u squared, which is 169, multiplied by our vector u, which is 5i minus 12j. And if you wanted to expand that out, you get minus 80 over 169i plus 192 over 169j. And if you want to look at it in decimal form, it's approximately equal to minus 0.47i plus 1.13j. So the reason for just checking that is that you can see that it is going in a negative x direction and a positive y direction. So it is kind of pointing up like something like that.